I'm Pam Blundell from the Institute of Psychological Sciences at the University of Leeds. Today I'm going to be talking to you about statistics, and particularly about null hypothesis significance testing, and why actually it's not the best method always for doing our statistics and our analysis. I'm going to start by outlining the logic of null hypothesis significance testing, and then I'm going to tell you about type 1 and type 2 errors, and finally I'm going to tell you about power and effect size analysis. In psychology, we're trying to answer questions about behaviour, and behaviour is variable. While we might want to know about cognitive processes underlying behaviour, we can't measure those cognitive processes directly. Therefore, we have to use behaviour and analysis of that behaviour in order to answer our questions about cognitive processes. One of the things we're trying to do is to establish whether differences between two populations are due to perhaps an experimental manipulation or a difference between those populations such as personality types, or whether it's down to chance or a sampling error. For example, we might ask a question such as, does caffeine help me learn? In order to address this question, we would first of all get two groups of people. One group of people we would give caffeine and another group we would give a placebo. We'd then run some sort of an experiment, some sort of test, to measure the abilities of those people. And then finally, we would have to look at the data that we've gathered from that test and run some analysis to determine if the caffeine has affected people's ability or if the measures that we've obtained are by chance. That is there actually a difference between those two groups' test scores? This means that we're setting up two hypotheses. We're setting up a null hypothesis, which is that there is not a difference between the groups, and any difference between groups has been obtained purely by chance. We're also setting up an alternative hypothesis, or H1, and this is that there is a difference between the groups that is due to our manipulation. On this slide you'll see that I've got two circles with numbers in. These represent some made-up data that we can use to illustrate our points as we go through talking about significance testing. So we have one circle with caffeine data and one circle with placebo data. And we've got 10 people in each group. You can see that I've calculated the means of these groups, and the mean of the caffeine group is 12 and the mean of the placebo group is 8. Now, by looking at the data, we might guess that there is a difference between the groups. But of course we can't just look at the data, we have to actually conduct some analysis. The analysis that we carry out is an independent groups t-test. I'm not going to go into the details of that test at this point in time. Here you can see the result of that analysis, and you can see that we found a p-value of p equals 0.000005. But what does that actually mean? Well, it means that there is a 1 in 200,000 chance of finding the result that we have found by sampling error. So that's pretty unlikely, and what we're likely to do in this situation is to say that we have found a significant difference between our groups and that caffeine is having a significant effect on people's ability in the test that we've administered. This means that we have rejected the null hypothesis. Now I'm going to talk about the errors in hypothesis testing and why it's not always straightforward to reject the null hypothesis in this way. So in the example I've just given, we rejected the null hypothesis. What sort of errors might this have led to? Here you can see a matrix which shows the different sorts of errors that you can make. Across the top you can see the situation if H0 is true, that is if the null hypothesis is true, or if H1 is true, that is if the alternative hypothesis is true. Down the side you can see what decision we make. So across the top we have the real world situation, down the side we have the decision that we make. If the real world, the null hypothesis is true, and we reject the null hypothesis, we are making what is called a type 1 error. So that is if in actual fact there is no difference between the populations in the world, but we from our sampling believe that there is a difference between the populations, then we are making a type 1 error, where we say that there is a difference between populations which is not true in the real world. The other type of error that we can make is clearly here. It's called a type 2 error. This is where we say that there is no difference between populations, but in actual fact there is a difference between populations. These are the two types of error we can make in null hypothesis significance testing. So what's the probabilities of us making these errors? Well, the probability of making a type 1 error is called alpha, and the probability of making a type 2 error is called beta. Alpha you're already familiar with. That was the value that I just gave you with the result of the t-test, where the p equaled 0.000005. That was the probability of saying that there was a difference when there wasn't really, a type 1 error. However, the t-test that we've just carried out gives us no information about the probability of making a type 2 error. In the example I've just given you, that's not such a problem because we found a significant difference. But what about in other data sets? So the probability of making a type 2 error is called beta. And from beta, we can calculate the power of our experiment. And I'll tell you something about that later. So the t-test that we've just carried out tells us nothing about beta. It tells us nothing about the power of our experiment. Here is another example. This time we've got again two circles, one containing caffeine data and one containing placebo data, but this time we've got 50 cases per circle. So we've got 100 people in our experiment. We've got a great deal more data. You'll also see I've calculated the means again, and the means are much closer. So the mean of the caffeine group is 23, and the mean of the placebo group is 23.8. Much smaller numbers. If we then carry out our t-test, we can see that there is still a statistically significant effect. There is still a difference between our groups. The difference is 0.8, it's a very small difference, but with group sizes of 50 per group, that's still statistically significant. The p-value is 0.009, so that's a less than a 1 in 100 chance of getting the result that we found by chance. Now you can see what happens if we only had 10 people per group. So I've taken 10 data points from each of those circles, so it's the same data and we've got the same means. So we've got the means for the caffeine group of 23 and a mean for the placebo group of 23.8. So we've still got the same size difference. However, this time, when we carry out our t-test, you can see that the p-value is 0.22. So that is approximately a 1 in 5 chance of getting the result that we've got by chance. Now, a 1 in 5 chance we don't view as being statistically significant. 1 in 5s happen all the time. So what's the difference between these two sets of data? What's actually going on here? What we have is we have a difference in the power of the two experiments. Power is the probability of detecting an effect if it is actually there. And obviously, we want powerful experiments. We want to be able to detect effects if they are actually there. The difference between the two data sets is in the sample size. Larger samples produce more powerful experiments. With a very powerful experiment, such as the one with 100 people in it, we can actually detect very small effect sizes. An effect size is a standardised measure of the size of an effect. How much of an effect is the intervention or the manipulation having? How big is the effect between our groups? While we may be able to detect small effects, and we may be able to find statistical significance with small effects are not necessarily significant in the broader meaning of the word. A very small effect might not be meaningful in the real world. In fact, Jacob Cohen, who has carried out a great deal of work looking at effect sizes and power, has pointed out that one of the problems of null hypothesis significance testing is that in actual fact, our null hypothesis is never ever going to be true. If you take two populations, it is always going to be the case that there will be some very small difference between them. And with very powerful designs, those very small differences can become statistically significant. We need to decide if an effect is actually significant in the real world, if it has any real world implications. So the very first example I gave you, where we had scores of 8 and 12, there was a 50% effect size, a difference of 50% between the groups. In the second example, with 23 and 23.8, we only have an effect size of about 3%, a very small difference. If drinking caffeine improved your test scores by 50%, I think you'd be likely to think about changing your drinking habits. If, on the other hand, it only changed them by 3%, it has much less of a real-world impact. But both of these effect sizes can be statistically significant if we have a large enough sample size. Luckily, we have statistical tools available to us that allow us to conduct something called power analysis. Now, there are two sorts of power analysis. There's an a priori power analysis, which we can carry out before we conduct an experiment in order to determine how many experimental animals or how many participants we need in an experiment. There's also post hoc power analysis, where after we've collected our data, we can examine how much power there was in our experiments and determine if our experiment was sufficiently powerful to detect any effects that may have been there. While the statistics to do this are quite complicated, there are lots of online tools now which can help us to calculate these, and I've just given you a link to one of them here. Feel free to go and have a play around with it. This software shows that in the example with 50 participants in each group, we have a power of 93.7%. That's a very powerful design. We normally try and design experiments that have got about an 80% power, an 80% chance of finding an effect if one is there. The experiment with only 10 participants in each group had a power of just around 25%. So that's a 1 in 4 chance of finding a result if there was a difference there. So that's a very, very weak experiment. It's really important that we design experiments to have an appropriate amount of power. If we have too many participants, then that's a problem in terms of the ethics, and it's also a problem in terms of having experiments which are too powerful. If we have too few participants, then we have experiments which aren't going to find anything, and that's a waste of everybody's time. So it's really important to understand power analysis and to understand effect sizes. So null hypothesis significance testing is still very dominant in psychology. It's still reported in all journals, and it still has a very important role to play. It's also important that we consider effect sizes. Indeed, more and more journals and grant awarding bodies are requesting power analysis and effect size analysis in their publications, so that all of this information is going to be available. And we need to think about effect sizes and power when we're conducting our research.